Testing, testing, 1, 2, 3, 4. Hey, some of you guys are early, that's fine. I just gotta tell you, we've been moving things around here inside the house, and I have painters behind me that will probably be making some noises, so I'm trying to see how audible everything is going to be if I try to turn down my mics a little bit. Can you guys hear me? Yes, I'll take that as a yes. Good. All right. Apologize for the delay there. All right, guys. So welcome back. You all managed somehow to finish both the quest portion of the exam and the free response questions. And for your class, I think I've managed to finish grading everyone's free response questions and posting a grade to Canvas. I just sent you guys an email a few minutes ago. I need to collate the free response question scores with the quest scores, and I haven't done that yet. After I do that, it's possible there would be a little bit of a curve, but from what I've seen so far, I'm guessing that pretty much we'll be able to use the straight scale that I advertised in the syllabus at the beginning of the semester. So, does anybody have any comments or questions about the exam? Anything you want to tell me about anything?
Dr. Rusin, is there a chance that at some point we could go over the second free response question?
Sure, we can do it now.
Awesome. Yeah, I was just kind of confused on it and how to go about the parameterization on that.
Right. Well, so, actually, I wrote out in an answer key that I just posted this morning, like 15 minutes ago, that you had multiple parameterizations that you could use. You always have multiple parameterizations that you can use for any curve or surface. And exactly how you're going to get those parameterizations, that's something of an art form. Parameterizing some curves and surfaces is actually quite tricky. In this particular case, I gave you a surface described implicitly. It's a surface that you can visualize kind of geometrically, and so there's a few different ways that you could go about it. And yeah, I'll summarize a little bit of how you can come up with some of these parameterizations. Actually, before I start doing the answer to that question, let me assemble all the other questions that you guys might have. Let's see, Malik, you have your hand up?
Yeah, so will we be able to see what questions we missed on the multiple choice section anytime soon? Because
Yes.
we can see the grade right now, but we can't like open up the actual like test and see what specific questions we missed. I was just wondering if that would be made available to us.
I didn't know it was not available to you, so I'm glad you asked me. Let me make myself a note here. Quest. You want to see actually what would be nice is if you could see the questions that you got wrong and explanations, like you do always in a homework, right? I mean, as soon as the deadline is passed on the homework, aren't you able to see explanations and stuff?
Yeah.
Yes, I'll see if I can't get that turned on. That's actually the first time I've ever used Quest for an online exam, so I don't really know how that stuff works. I will certainly look into that. Oh yes, that just reminded me of something else. I have to get you guys a new homework as well. Correct me if I'm wrong, but you are currently not working on any homework, right?
So is it going to be one last homework?
Yes, that's my thinking. There should be one last homework all over the remaining topics. We have one more section really of chapter 7, and then chapter 8 is where all the big theorems come together. So I'm gonna be setting you guys up for that today, I hope. So yes, we'll have one last homework. We have, I guess, 2 weeks of classes. Is that correct? Today is the 27th, 27th, 29th, and the 1st. And then, yeah, and 3 days next week as well. So 2 weeks left of classes. Part of that, I'd like to use that for review if we can. And then that'll set us up for the final exam. I'm going to try to do the final exam the same format, I guess, as this midterm exam that you just had. So actually, before I get to answering the question that was asked about the second free response problem, let me also talk to you guys about the, you know what, actually I'll wait on that. I do want to find out from you guys how it went to take the questions and the free response at the same time, but let me deal with the subject matter of the second free response question first, and then we'll turn to the sort of the mechanics of test taking. All right, so let me turn the camera on and get started here. What's that? All right, so the second pre-response question was asking you to find the surface area of a certain surface. And of course, the formula for the area of the surface is that you should get that by just integrating the constant function that's always equal to 1 over the surface, and you computed an area integral. So that's the way to begin these problems. And then, of course, the very next step obligates you to find a parameterization of the surface. Now, as I said in the answer key, you guys came up with several good parameterizations. So a cluster of you realized that you could just think about this surface as being given explicitly, where you think of it as the graph of a function of 2 variables. Specifically, in this case, it would be that z is equal to the square root of x squared plus y squared. So you simply take the formula that I gave you when I described the surface implicitly, and you take this equation and solve it for z. You know what, I'm going to put my little picture in here that I had at the beginning of the semester, where we talked about the 3 ways that you could describe a surface, or a curve for that matter. Where we began is right here. I described the surface for you by giving 1 equation and 3 unknowns. 3 minus 1 is 2, makes it a surface. So this is where you started. Unfortunately, in order to calculate the integral, you have to end up over here at a parametric description of the surface. And I never gave you a way of going straight like that, because frankly, I don't know a good way to go straight that way. My general technique for getting a parameterization of a surface given implicitly is to first write it explicitly, which is what I've just done up here. And then once you have a surface, or a curve as well, given explicitly, you can go straight down to giving it parametrically. I've called this like the cheater's parameterization, where you let your 2 parameters, u and v, simply be synonyms for the 2 input variables for the function, and then the output variable is just given by changing the names of the variables in the function that you're graphing. So this would be the transformation that you're using. Of course, you also need to think about the domain of this transformation. What inputs do you need to apply? What input pairs, u and v, do you need to apply this transformation to, so that you end up with exactly the graph that was given? And the answer is, it's the u's and v's that you need are exactly the x's and y's that you had, that you graphed. And in this case, if you think about the cone as being the graph of this function, it's only the portion of the graph that lies over this disk. So this would be my domain D down here. This is the set of x's and y's, or equivalently u's and v's, that you need. So you would turn this surface integral into an integral over this set D. You change your domain of integration from the floating surface into this portion of the UV plane. And of course, you rewrite your integrand, but in this case, there are no x's and y's to substitute away, so the integrand will still be a 1. And then you have to go through the t sub u and t sub v thing to figure out how to adjust the what's called the differential. But I have pointed out to you guys that in this case, where the surface has been given explicitly and you went to this parameterization, then the little fudge factor, the tu cross tv thing, I can save you time because it'll always come out to be the same. It'll always be the square root of 1 plus the sum of the squares of the partial derivatives of the function f. And so, you know, you differentiate this. The partials with respect to x and y are x over the square root and y over the square root. And magically, when you add up everything that's inside the square root symbol, this comes out to just be a 2. So now you're integrating 1 times the square root of 2 over the disk. That's a constant function over a set, so it'll be that constant times the area of the set, and you know the area of a disk, so you're basically done. So all of that is to say, if you notice that you're starting here and you want to get here, at least a route that you can proceed by is to go this way and that way around the triangle. Others of you took advantage of the other coordinate systems that we had that led us to discuss not just a triangle, but two triangles at ends of a prism. So I think this is a good time to remind you of how the transformations can go. If you want to use Cartesian coordinates, you can describe the surface explicitly, implicitly, or parametrically, but you can do the same choices in any of the other coordinate systems that we've discussed. For example, you could work in cylindrical coordinates or spherical coordinates. And well, now you have 6 different ways of presenting a curve, and I'm drawing these line segments to remind you that you can go back and forth. At least to some degree, it's possible to go back and forth between these different ways of presenting the curves. So I've already talked about how you go from here to here. This is us just solving for z. And going from here to here is that would mean just moving everything from one side of the equation to another. Going from here to here, I've given you a sort of the cheater's parameterization. We've also talked about how to go from here to here. This is the one, and I haven't used it yet today, this would be the one that would be called elimination. You eliminate the parameters, the u's and the v's, right here. If you eliminated u and v from these equations, instead of having 5 equations with 3 letters in them, you can have just one equation with 3 letters. Namely, you just get rid of u and v from those 2 equations, and then you'll have this equation to relate just the x, y, and z. So we've talked about going around this triangle in different directions, but we've also tried to go back and forth between presentations of the same curve or surface in the different coordinate systems. We started right here, but it's very easy if you are here to go this way and get an implicit description of the same surface in a new coordinate system. Because if you know that your curve is given by a single equation in Cartesian coordinates, but you know how to express the Cartesian coordinates in terms of, let's say, the spherical coordinates, then you just shove in the formulas for x, y, and z into those spots, and what you will get on this side will be an equation that links rho and theta and phi, if I'm using spherical coordinates. So I guess, let's see, z is equal to rho times the cosine of phi. So it would be rho squared times the cosine of phi squared. And on this side, if you work out all the trigonometry of the spherical forms of those 2 variables, you just end up with rho squared times sine squared of phi. And when you divide by rho squared and take the square roots of both sides, you discover that cosine of phi is equal to sine of phi, and the only way that that's going to be true is if phi is equal to pi over 4. So you went from an implicit description in Cartesian coordinates to an implicit description in spherical coordinates, which managed to simplify a whole heck of a lot. And then, just as I went from that corner to that corner, I can go from this corner to that corner by solving for one of the variables in terms of the other 2. Well, there it is. Phi is already solved for. And just as I went from this corner to that corner, you have an easy way to parameterize a surface that's given explicitly in spherical coordinates. If it gives you, let's say, phi as a function of the other 2, then you let the other 2, the rho and the theta, be just synonyms for the u and the v, and then phi is whatever it needs to be in terms of rho and theta, which in our case is just constant. So now you've got a parameterization in spherical coordinates, and here is another one of the edges that's easy to traverse. If you have been given a parameterization in spherical coordinates, then that gives you a parameterization in Euclidean coordinates. Because if you have formulas for rho, theta, and phi, then that gives you formulas for x, y, and z. I mean, z, for instance, is supposed to be rho times the sine of phi, excuse me, cosine of phi. So now I have a formula for rho, and I have a formula for phi. Oops, yeah. So that, presto, that gives me a formula for z. So I started here, I went here, went up there, came down here, and went over here to get a parameterization. That actually took me through every one of these corners except for that one. So it is just a different way that you can use a different coordinate system to end up with a parameterization of your surface. And I used the spherical coordinates on this back part of the prism. If you had done exactly the same process in cylindrical coordinates, you would get yet another parameterization of the cone. Actually, it would be pretty similar to this, but all of these turn out to be a 1 over square root of 2, and they just kind of disappear. Well, I said a little bit more about it in the answer key that I just posted. So I realize that it is sometimes difficult to get these parameterizations, but if you focus on the fact that you have been given a surface somehow somebody gave it to you, some coordinate system, they must have either written something down explicitly, implicitly, or parametrically. And well, I tried to prep you earlier in the semester about how you can move around in these triangles or prisms. So if you know which vertex you're starting at, and you know where you ultimately want to end up, all I can say is use the tricks that I've given you that take you from one corner to another of this little prism. So I forget who asked me for clarification on this free response question. Is that portion of the problem clear about getting the parameterization? And then secondly, I guess I need to ask, do I need to say more about that problem besides the parameterization?
How did you get your rho equals u and theta equals b?
Here?
Yes.
Well, that's because I realized once I had gotten to this point, I was now presenting my surface implicitly in spherical coordinates. In other words, what is written down is a single equation that uses all three of the variables. These variables, I mean, rho, theta, and phi. And I simplified the equation. Of course, you always try to make them simpler, but it's still one equation and three unknowns. It says phi plus no rhos and no thetas is equal to pi over 4. So there's one equation, three unknowns, 3 minus 1 is 2. That's fitting for a surface. Then how do you go from this corner to this corner? Well, that's always a question of solving for one of the variables in terms of the other two. Well, from this equation, the only one that I feel I can solve for is phi. I move this stuff to the other side of the equation, and now it says phi is equal to pi over 4 plus 0 rhos plus 0 thetas. And I know it looks too easy in this case, but it fits the format. You're giving one of the variables as a function of the other two, same as I did here. That's what it means to give a surface explicitly. And then once you're in this corner, the way you come down to a parametric description in the same coordinate system is to just be lazy. You introduce two new parameters that are the same as the other two variables in your coordinate system. And then you let the third variable, meaning the one that's on the left side of such an equation, you let that third variable just be whatever the formula dictates when you replace rho with its synonym and you replace theta with its synonym. And in this particular example, neither the rho nor the theta actually shows up. So my formula involving u's and v's is now just a constant. It's pi over 4 plus no u's and no v's. Right? I mean, I know it's irritating because it almost looks too simple, and it is simple because that's what makes a cone be a cone. Guys, if you remember what spherical coordinates measure, you know, rho is your distance from the origin and theta is an angle of a certain plane, but phi is the angle that you move down from the positive z-axis. Well, when you think about what a cone is, that cone is precisely all the points that you can get to by starting on the vertical axis and then drooping down by an angle of pi over 4. So you shouldn't be too surprised that the cone is presented so simply. So that's my parameterization of the surface in spherical coordinates. And then, like I say, I use the formulas that express Cartesian coordinates in terms of the spherical coordinates to now express x, y, and z as functions of the u and the v. I am trying to make sure that you guys see this as a general process so that you know, you're ready to handle some more complicated surfaces in the future. But, you know, this particular example, it is kind of like really simple to express in either cylindrical or spherical coordinates as well as Cartesian. So, you know, it's not really all that hard to get some of these parameterizations just by kind of eyeballing it. I mean, I have to say, a lot of people just kind of wrote out a formula that said phi of u comma v would be u cosine of v comma u sine of v comma u. And, well, that's exactly the parameters. I don't know what's happening to my camera. I apologize. I don't know exactly where people got this formula. You can get it by going through exactly this process, but using cylindrical coordinates instead of spherical. Or you could just say, you know what, I need to have 3 formulas involving u's and v's that make this equation identically true. And the easiest way to do that is just experiment with some trig functions, and sure enough, you'll see that the square of this plus the square of that matches the square of this. So, I don't know, what else should I say about these parameterizations?
So I had a question about that, the last example. So how would you go about finding the area element?
Yeah, once you have your parameterization, I don't know why I'm calling it phi today. Usually I call it capital T. We've discussed this issue that, you know, you take the 2 partial derivatives, end up describing the vectors on the edges of little parallelograms that march around on the surface. And then the cross product of those, the magnitude of the cross product of those parallelograms will give you your area element. So what you would need to compute is the T sub u and the T sub v, that those are actually the 2, no, let me just call it, they'll be the 2 columns of the derivative matrix. So I differentiate this function of u and v, the component by component. I'll write down the gradients in the top row. Here's the partials with respect to u and with respect to v. For the next one, the partials with respect to u and v. And the last one, the partials with respect to u and v. So the first column is your tu, the second column is your t sub v. When you compute t sub u cross t sub v, you get the following vector. See, the first component just turns out to be minus u cosine of v. The second component turns out to be minus u sine of v. And the third component is just a u. I think I did that correctly. So now the magnitude of this is where your area element is. It'll be the square root of the sum of the squares of these 3 components. But here's a u squared at the end, and the sum of these 2 squares will be u squared times cosine squared plus sine squared, which is 1. So really you just have 2 u squareds in there, and the square root of that is absolute value of u times 2. Well, in our case, our u's are all positive anyway, so it would just be u times root 2. And that's the thing that'll multiply the du dv, and then you'll integrate just that with respect to u and v over the domain of this parameterization. I think you can see that you need v's to go from 0 to 2 pi, and the u's in our problem go from 0 to 3. The u's are the same as the z coordinates. They go from 0 to 3.
Brianna, does that answer your question there?
Kind of, yeah. So usually for like cylindrical, the area element or the dA is RdRd theta, right? So I was just like, that was one thing that kind of threw me off, was that you didn't use that extra R.
I don't, well, this is the R in a sense, right? Because the R is the thing that you'd be multiplying in here. So the R is in there, but why the extra square root of 2? That's the real question. But it isn't really a question, because when you say, hey, wait a minute, I thought we had this conversion factor for cylindrical coordinates that said you just do R d theta with no square root of 2 in there. You're right, but that's the volume element in cylindrical coordinates. That's the one that says you'll take R dr d theta dz. And that was more pronounced, I think, for the people who are trying to do things in spherical coordinates. For them, they kind of memorized that it's, I actually don't remember, it's rho squared times the sine of phi. I actually don't remember the one for spherical coordinates, but that's a volume element. That's what I'm trying to emphasize here. Oops, yeah, theta and phi. You're not computing volumes here. That's why I'm a little nervous when students tell me that I'm going to compute this surface integral in spherical coordinates or in cylindrical coordinates. I would really rather not have you do that. I would prefer that you use the language I did here, which is to say, look, in order to compute this surface integral, I need a parameterization of the surface I was given. You have to parameterize the surface in the coordinate system where it's given. You can use the different coordinate systems because all of the points on our surface have 3 Cartesian coordinates and 3 cylindrical coordinates and 3 spherical coordinates. But at the end of the day, your parameterization just has to involve 2 letters. So yeah, thinking about the coordinate system that is around the surface is fine, but I see you've already indicated how you're getting yourself caught, and you're missing this factor of a square root of 2, for example, because you're confusing the transformation, the fudge factor that shows up that says how volumes are adjusted. That's not the same as the fudge factor that says how areas are adjusted. When you transfer u and v coordinates from the uv plane onto our surface, then the areas will be stretched by this vector. This is the formula that tells you how volumes are stretched when you move from a chunk of r theta z 3-dimensional space into 3-dimensional space. So you had the right formula for a different problem. Am I making that clear?
Yes.
Okay. Yes, I had quite a few students that got caught that way. They knew they wanted to somehow take advantage of a different coordinate system, but they whipped out the volume element instead of an area element. Other comments on that question? Okay, how about questions on the other free response problem? That was the integrating over the diamond. I think people did pretty well. By far the most common error there was a lot of people forgot the absolute value bars around the area element. I even put them in here just to remind myself that they were supposed to be part of the calculation, but you can drop them once you know that the thing inside is always going to be positive, but in general it's part of the story. I guess I could also ask about if there were problems on the quest questions that I gave you. By and large, you guys seem to do pretty well as a class. Quite a few of you even got everything right. I think there was only one question where it wasn't an overwhelming success on one question, and I think that was the one about line integrals. You can be forgiven there because that's the most recent topic that we've been discussing. All right, if you guys don't want to ask anything about the particular questions on the exam, talk to me about the mechanics of it. You seem almost everybody managed to figure out a way to scan their papers and upload it to Canvas. So that, I'll take that as a success. Any objection to doing that again for the final? Okay. How about the, how long did it take you to actually go through all the questions? Were you able to finish the quest questions in the 2 hours?
I guess one thing that I would say is if you were able to like make the quest test a PDF, like a slide. I don't know if that's possible because that was a little like difficult to like funnel through and make sure that like and keep track of time. So.
Yes, I did notice that. I thought it would, in fact, have come up to you exactly the way a homework would have come up. But you guys, yeah, it presents you one question at a time on the slide or something. Is that right?
Yeah.
I can. Well, yes. At the very least, I can do the following. I can give you guys, since I know now that we've done it once, I know how to make the exam come at you the way it did. I can give you, in addition, a PDF of just the questions. I guess I can have that all available at the same time. So if you want to print that off or something and just have it off to the side, or maybe print it off and then or keep it on your screen and work the questions and then sit through the, sorry about the camera here, then sit through the process of taking the exam. Let's see if that's a little more stable. Sorry about that. Oh, somebody asked where the answer key is posted. I sent you an email, and I thought I put the link to it in there. Also, if you go to the syllabus, in the syllabus, there's some boldface stuff about the second midterm exam, and I put a little link at the end of that boldface section. Malik, what's up?
Yeah, so also just with the exam, the multiple choice portion, one thing I personally like was having some trouble with was you couldn't really like once you submitted your answer, you couldn't go back and change it or check it. Like, so I mean, obviously that's on me. Like I should have realized that and not put my answers in. But like it would have been nice to like have seen like a PDF form so you could see like go back and just check your work and like see all the problems and go over what you felt less confident about. Like once you had everything submitted, you couldn't really do that. So like once you had like set your answer in, it was kind of like, there's no going back. And I personally felt like, I mean, I'm someone who likes to check my work. And so
yes, I'm glad you are. Yes, actually, I do apologize there because I didn't know that was the case. I honestly thought that you guys could enter answers and then click again and it would erase the previous answer and try another one. And I didn't think that they would stick until you hit submit or something. That will be another thing that I will talk to the Quest people about. Again, when you do the homeworks through Quest, is it the same way that as soon as you click an answer, it comes back and it says, no, that's not right, try again? Or
yeah, that's how it's formatted. So
as soon as you click something, it's entered.
Yeah.
Clicking
you have to like click submit. So you could like select that you have a like response, but you can't like move forward when it's in slide mode. Like unless you either select submit or it clears the answer for you. I do think like if it's a PDF, like if we do get a PDF version of the test, it would be easier because then it'll still count it as like the one-time response that you're like wanting for the test.
Right.
But we have like it in front of us, so we don't have to like keep cycling through the slides and make sure that we're covering everything.
Okay. Yes, good. Those are all good suggestions. like I said, I've never actually done this one before, but I can certainly fix all of those for the final. I will get you guys a PDF. How much time did you spend on the free response questions? Because I did notice that an awful lot of them were coming in at like, 1:58 p.m. with a 2 o'clock deadline. Did you feel like you had adequate time with 24 hours to answer the 2 questions along with the quest?
I honestly spent more time scanning the files,
Yeah.
or scanning the papers and like writing them out neatly, than I did actually working on the questions. I felt like they weren't too bad at all in terms of time.
By the way, I do appreciate you guys having taken the care. Most of you actually presented me with something that was fairly easy to read. I mean, unlike the typical exam where stuff is just kind of scribbled, you guys had kind of laid out your answer in a readable format, which made it much easier for me to grade. So thank you for that. It's good professional attitude. When you're taking your higher math classes, that will serve you well. And yeah, I thought people might have some trouble with the scanning and so on. I set up, I don't know if you guys even saw it, I set up a dry run assignment to give you a chance to try going through the scanning and everything, and only a few of you took advantage of that. So, well, you made it work at the end, so I'm glad that came out okay. All right, well, we will have a final exam, and I'll do pretty much the same format, I guess. Everything worked the way I wanted, except for the fact that there's no way for me to control cheaters, and I'm sorry to say I think I spotted some, so I don't know what to do about that. But anyway.
Dr. Wilson?
Yes, go ahead.
So for the final exam, is it going to be during our scheduled time for the class? I think it's 7 to 10 on a Saturday night.
Yes, but what I'm going to do is, I guess, the same thing that I did for this exam, is that I took advantage of your scheduled hour, but I added in a whole bunch of extra time for people who are on different time zones. So, it'll be, if you want to just sit during exactly the same time that we were scheduled to have an exam, that should be fine, but I'll also set it up so that you can give yourself a different time period.
Okay, so it's probably going to be available 24 hours prior to our
schedule. Yeah, I mean, and, nominally this was supposed to be a 1-hour midterm, and I gave you 2 hours even just for the quest portion. So the final is supposed to be a 3-hour exam. So, I guess I can open up quest for like 6 hours for you, and I'm sure nobody wants to sit for 6 hours, but I'll give you plenty of time. They're being really quite emphatic with us, and I agree 100% that we need to reduce the amount of what they call synchronous requirements for the course. I know that not everyone can be here. We have actually only a third of the class is tuned in right now, but plenty of people chime in later. I see who goes to YouTube and stuff, and so I'll do the same thing for the exam, give you the option of choosing what time you're going to work.
So, I guess since the exam, like the final exam is supposed to be about it's 3 times the amount of time. I mean, you're going to increase the amount of questions as well, like for both Wisconsin. Yeah,
usually my final exams are about twice as long as my midterms. So if it's nominally, it's a 1-hour exam for a midterm, and I know people they want more time. But so if I make it twice as long, then 3 hours really ought to cover it. And usually on a final exam, people tend to leave. They're either done or they're just exhausted. So if I give you 24 hours, I'm hopeful that that'll be enough for you. All right. You want to get back to doing some math now? We've used almost all of our time. We have 10 minutes left. But let me set the stage for what we're doing with the last section in this chapter 7. So I'll spin this around again. So what we did, as we worked our way through line integrals, we did them in 2 stages. First, we talked about just integrating a function that was a scalar valued function on a curve. So I would give you a function. First, we started off with a function that was defined, let's say, over three-dimensional space, but it spat out real numbers. And then I would give you this curve that wound through space, and I ask you to integrate that function over the curve with respect to arc length. And you know what that means, at least conceptually. You chop the curve up into little pieces, and you multiply your length times the value of the function. The value of the function is a real number, so multiplying a real number times the length gave you a number. Add up all those contributions and you get a number. That was path integrals. For line integrals, we started off with a vector field. So at each point, I actually had a vector. But we came back to this framework because there was a particular number that I always wanted. I always wanted you to take the dot product of that vector with your unit tangent vector. I'll put a little arrow there. I'll put arrows on both of those. How about that? So in other words, that took the magnitude, which is a number, takes the magnitude of the force, but it reduces it by this cosine, where theta is the angle between where you're going on the curve and where the vector field points. So that would have been this theta in here. Okay, so after you now had, this is just a real number, after you now have a real valued function, you're right back into this setting. We did have a little bit of an issue because we had to say, hey, there's actually two unit vectors that are tangent to the curve, and we need to decide which one of them we're talking about. And that came from picking what's called an orientation on the curve. That just basically says, are you going forward or backwards? Are you going from left to right or right to left? And this had very natural consequences. I mean, this is exactly the kind of thing that you would need to compute in a physics setting. If this was a force, and this is a direction of motion along a curve, then this quantity would represent the amount of work that you're doing or the work that's being done on you, depending on which of those two tangent vectors you refer to. All right, our next trick is going to be to do a similar sort of two-stage thinking where we replace the curve by a surface. So this is, can I put the word was here? So that's what we have been doing on curves. And now, for surfaces, it's going to be the same two-stage deal. I'm going to start, we have already started off with the assumption that we've got a function defined at each point in space that gives us a number. And then when somebody hands you this surface, you know how to interpret this quantity. This says you chop up the surface now into little bits. You multiply, I guess I write dA usually. You multiply the area of each little bit by the value of this function. And again, the value of the function is a single real number. Real number value here. The area is also a real number, so you just get real numbers coming out. What might you be interested in if you had a vector field floating around? So an example of this would be, imagine that you have a flow of water in a river. So here's it's supposed to be sort of a chunk of the river flowing downstream. And there might be little eddies in the water where the water's kind of spinning around. There could be hot and cold areas where the water is rising and falling. Right? So at every point, you can measure the flow of the water. That flow has both a magnitude and a direction, so it's a vector. Now, what could you possibly be doing with a surface that's suspended in space where you have this flow going past it? Well, what you might want to measure is something like, I want to measure somehow the stuff that's being caught by this. So if this was going to be the front face of some kind of drainage pipe, then I would be able to be calculating how much water came down the drainage pipe if I compared the flow of the water to the surface that indicates the front. You might want to think about this as the capital F is measuring the flow of how many fish swim past at each given moment. So you have this vector is giving you both a direction of the flow of the fish and a magnitude, a quantity of fish that goes by. And then this surface becomes a net, and you're trying to count how many fish will be caught by the net. More historically, what you might have is this F might represent some sort of magnetic flux or an electric flow field. And then you have here a membrane made of metal, and you're trying to capture the amount of electricity that's flowing past it or something. The key thing is that the quantity that you're going to be adding up at all points will end up being a number, but it's a number that you compute from that vector field. Specifically, the number you're going to get now will take that vector field and take the dot product with a vector, a single vector, at each point on the surface. And the vector we want now will be a unit normal vector. Here we were looking at a unit tangent to a curve. Now we want a unit normal vector to the surface. So in the case of, let's just take a flat surface where you just have a rectangle, a flat rectangle in space, then you draw a single unit vector, n, that's normal to the plane everywhere. And then if the flow is coming in at angles, or perhaps different angles at different places, then the amount of the flux that you actually feel is going to be reduced by the cosine between the flow of the vector field and this unit normal vector. We measure an angle theta in there, and it will be the magnitude of F reduced by the cosine of this angle. So I'm using the same notation here, but do notice that there's been something changed. The unit vector in question is now perpendicular to the surface instead of being parallel to the curve. Okay, a curve only has one dimension anyway, so there's really only one direction that is somehow associated to the curve, whereas a plane is already two-dimensional, and I don't know what other vector would ever show up in a natural way. So you could play all kinds of mathematical games where you take the vector field and you do something else to create a single real valued number, but I don't think any of them would be useful from a scientific point of view, from an engineering point of view. This, on the other hand, this captures something of real interest to us. You could see that if you're trying to catch fish, you kind of want to make your net be more or less perpendicular to the flow. If in that same stream, here's the same stream, I'm trying to draw the same thing again. If you put your net this way, then all the little fish would swim right past and you get nothing. And the reason why is because in this case, the normal vector to the surface is perpendicular to the flow of the fish. And so the dot product comes out to be 0. All right, so with this in mind, what we're going to do in this remaining chapter is compute surface integrals that arise from a vector field. And because of the historical interest from the scientists and the engineers, what we're going to choose to do is to make a function little f by taking the dot product with a unit normal vector. Okay? So, of course, we'll have the same kind of issues that we had for curves. Where are we going to get this unit normal vector? I mean, what you could do is if you could get any normal vector, I'll write it with a capital N for a moment. You could take any normal vector and then divide by its magnitude. That way you'd get a unit normal vector. And now if you call that the function f, then I know how you're going to go about computing the value of the integral. This thing that we will write as the integral of f dotted with n, you'll see this notation. It has now been rewritten as it's the integral of f over this surface, so we know how you're going to compute it. What you'll have to do is to parameterize the surface. So I'll write it the way we've been doing it. However you parameterize it, you'll parameterize it over some domain D, and you'll have to substitute away all the x's and y's and z's that are in this expression, change them all into u's and v's. You'll have to multiply it by this expression of u and v and integrate with respect to u and v. Here's the thing. It is a great gift from nature that, in fact, if you want to have a vector that's normal to your surface at any point, the way to do it is to take those two tangent vectors and compute their product, their cross product. The cross product of any two vectors is in fact perpendicular to both of those vectors, which means you can use that cross product as your normal vector. And when you do that, you will have the magnitude of this vector in a denominator and here in the numerator. So exactly the same magic that we had for curves is going to happen again for surfaces. And you get those two factors with the magnitudes disappearing, and you'll see all you need to do is to take your vector field at each point. You will have to stick in the formulas for x, y, and z into there, and take the dot product with tu cross tv. And that's what you'll integrate with respect to u and v. So I'm going to stop here because we're out of time. But these will be the things that we do next time. And you will see that we really are computing the same kinds of surface integrals as before. But typically, we don't bother going through the process of writing out what f is, because nature has made it a lot more efficient to just compute this, this dot product. And that's the way we usually compute those surface integrals. Okay? So, any other questions? There's somebody's asking about the homeworks. I think I mentioned earlier, I will put up another homework for you. I guess it will be due, I'll make it due, I guess, at the end of next week. Since it's the last one, I'll have it due on the last class day. Anything else?
Does it matter which normal vector you're talking about? Because like with surfaces, there's like one pointing in one direction, and then there's the normal vector pointing in the other, and then
yes,
it's like...
exactly. You very much want to choose the appropriate choice. So just like for curves, you had two different tangent vectors. In the case of a surface, you'll have two different normal vectors to the surface. And yes, if you want to measure the number of fish that are caught, you better choose a normal vector that's going to make it seem like it points more or less in the same direction of flow, because you want to represent a positive number as the number of fish you're catching. So yes, this amounts to what we say is we're choosing an orientation for our surface. Just like you choose an orientation for the curve, are you going this way or that way? On the surface, you should say, hey, do you want me to count the flow, when the flow goes past the surface this way, do you want to count that as a positive or a negative? It's your choice, and you need to make sure that you choose the one that matches the physical applications. In terms of the formulas I'll write down, it kind of matters as to, did you want to take tu cross tv or tv cross tv tu, because you'll know that those will be negatives of each other, those two vectors. So that is an important question, and we'll have to address that. But the answer, in short, is going to be, it depends on the application. All right, guys, I'm going to call it here, and then we'll pick up and we'll start to do some of these calculations on Wednesday. Okay? Thank you for coming in, and let me know if you have any questions on your exam.